Here we have the formula to compute the arc length of a curve. So if we are given a curve correspond to the function y equal to f of x, so we want to compute the length of y equal to f of x for x between a and b. So the length of this arc, then the formula is that if f prime, so the derivative of f is a continuous function on this interval, then the length of the curve y equal to f of x, where x between a and b is given by this formula, the integral from a to b of square root of 1 plus f prime of x squared dx. So we want to understand why we have this formula. So to compute the length of this arc, the strategy is as we have done for computing the area, the volume that we have done before. So we create a partition of AB by slicing the curve. So we cut the curve into the smaller pieces and we compute the length of each piece. And now let's cut this curve into the small pieces like this and look at what happened in one small piece. So for example, let's look at this piece here. So let's look at the graph here. X, y. We have y equal to f of x, where x from A to B. We want to compute the length of this arc or this curve. So as we have done before, we create a partition of the segment A and B, each of width delta x, and we look. So we cut the given arc into smaller pieces and we compute the length of each pieces and we take the sum. And by doing the very fine partition, so making delta x tend to 0, we can approximately the sum of those infinitely many smaller pieces into the. And by taking the limit when delta x tends to 0, we get the length of y equal to f of x. So now let's look at the length of one piece like that. So for example, let's look at this piece right here, this one. So here would be x. Let's say this value is x, and the next one would be x plus delta x. Then we have this length is delta x. This is f of x. This corresponds to the point x f of x. So the y coordinate is f of x, and this point corresponds to f of x plus delta x. So this length is delta y. We can approximate the length of the arc y equal to f of x, where x between x and x plus delta x by the length of the hypotenuse. So here we have a right triangle. Then the length of this piece the length of the hypotenuse is the square root of delta x squared plus delta y squared by the Pythagorean theorem. And by taking the sum of all those small segments, we get the approximate length of the curve y equal to f of x. Okay. Inside we have 1 plus delta y squared divided by delta x squared. And this one, we can bring delta x squared outside of the square root. What we have is delta x times square root of 1 plus delta y divided by delta x squared. Now, if delta x tends to 0, what we see is that this is dx. Delta x tends to 0, we have dx times 1 plus dy divided by dx square. So by taking the sum of all those smaller pieces, we approximate the length of the curve y equal to f of x, where x runs from a to b. And when delta x tends to 0, that Riemann sum becomes the integral. So we have the integral from a to b of all those small lengths. So the length of the curve we need to compute is the integral from a to b of this quantity. So we can put the x here. Inside we have square root of 1 plus dy over dx squared, and dy divided by dx squared is actually the derivative of f prime of x. Dy divided by dx, we have the f prime of x squared. So this is integral from a to b square root of 1 plus f prime of x square dx. So this is exactly the formula we try to understand for the arc length of the curve.